Hi, I'd like to talk about the concept of power and take a look at an example of the mechanical power of work. Now, the rules of energy are not typically expressed in the first introduction as necessarily being functions of time. In fact, in a lot of cases, we're just taking a look at positions and velocities as they are right now. Well, if we wanted to incorporate a sense of time, that's where we get into the new idea of physical power. And power is defined to be the derivative of energy with respect to time. So it could be any form of energy transfer. It could be any of those six pieces that we've talked about: work, heat, mass transfer, mechanical waves, electromagnetic radiation, electrical transmission. All six have a power associated with them, and they'd all be the derivative of the transfer of energy with respect to time. So for units, the unit we use for power is the watt. And a watt is 1 joule of energy being transferred per second. And in English units, we have the horsepower. And 1 horsepower is 746 watts. So this is probably one of the biggest cases of symbol collision that we find in physics. When we go to take a look at the power from work, which is measured in watts, is the derivative of work with respect to time. So a couple of reminders. If it's a unit, it follows numbers. So W, capital W as a unit, is for watts. If it's an idea, a concept, shorthand in a symbol, capital W in an equation is for work. Now, a couple of other contextual clues you'll see in nearly every textbook. Units are always written in the same font as the numbers that follow. Symbols from mathematical equations are almost always in italics. So if it's a W in italics, which is hard to do on a board to write in 2 fonts if you don't have great handwriting, but W in the context of an equation, work, W as a unit, watts. Let's dig in a little bit more to this idea of taking a derivative of work, because work we defined through an integral. So if I have a differential amount of work, a tiny, tiny, tiny piece of work, well, we said that that differential amount of work is equal to our force dotted with a path element, dr. So if I plug in what I have for a differential element of work to my differential element of work in the numerator, I have the force times a differential path, dot product here, divided by my scalar differential time element. Well, dr dt is just the definition of velocity. So the instantaneous power done by work is equal to the force being supplied times the speed at which that force is moving with the system as it does work. So let's take a look at an example. Say I have an 18 horsepower motor and I'm trying to tow a car that's stuck in the swamp. And the car has a mass of 1,200 kilograms. There's a force of tension in the cable of 4,500 newtons, and in theory, I want to try to pull this car moving at a speed of 2.5 meters per second. Is that doable? Well, if I take a look at my power equation, the power needed would be my force of tension times the velocity, and since that tension is necessarily being applied in the direction of motion here, the dot product is just going to be the magnitude of force, 4,500 newtons, times our speed, 2.5 meters per second, which gives me 11.3 thousand newtons, 11.3 kilonewtons. So, in terms of horsepower, I can divide 11,300 watts by 746 watts per horsepower, which gives me 15 horsepower, which is less than the 18 horsepower maximum, which also means we could get an acceleration. So if we wanted to calculate an acceleration, we could think about the maximum power, because the maximum power would equal the maximum force we could deliver times our current velocity. So the maximum force then, as long as things are in the same direction, would just be our maximum power divided by the current speed. And that force would equal the mass of our car times the acceleration that we're going to get, plus whatever force is currently being delivered by that motor to that object. So if I solve for that acceleration, I can subtract this current force from both sides, so I'd have the maximum power divided by the current speed minus the current force that's being supplied, and then I'd divide both sides by mass, and I could calculate this out, but I could also simplify things just a little bit by multiplying and dividing that term on the right by the speed. The current force times the current speed is the current power, which we just said is 15 horsepower. So mass times velocity, I can keep that by itself in the denominator, so the maximum power minus the current power means I have 3 extra horsepower available. Divide by the mass of 1,200 kilograms, divided by the current speed of 2.5 meters per second, and that means I could have an acceleration of 0.75 meters per second squared. Thanks for watching.